Good afternoon, everyone. Welcome to the McGill and CIRRELT Transport Seminar. It's a pleasure and an honor for sure to welcome Professor Amer Shalaby from University of Toronto. And we are really lucky that he agreed to come and give us this talk right after finishing his class. So he's really generous for his time. And thank you so much for coming, Amer.
Okay, well, thank you so much, Ahmed. And hello, everyone. Thank you for having me. And I'm glad to be here with you to share with you some of our transit research work, specifically some research related to AI applications to public transit. My agenda is very simple. I'm just going to start with one motivational slide. And then I'm going to spend the bulk really of my presentation talking about three streams of research about different applications of AI to transit. And then I'm going to have some concluding remarks and thoughts about really what we have learned and what AI is good about and what it's not. I aim for maybe 45 minutes, and then hopefully we'll have plenty of time to answer any questions, or you can share your comments as well. Okay, so transit agencies, it's no secret, has been really swimming in transit data for so long. The AVL, the APC, and the AFC data are just overwhelming transit agencies over and above what really conventionally they have other kinds of data like household travel surveys, rider satisfaction surveys, and so on. Since I was a student, and that's really many, many years ago, this has been always a problem, or has been always really shared as a problem that, transit agencies have a lot of data, they don't really know what to do with it. So unfortunately, much of this data really goes to, I wouldn't say waste, but really it's not being utilized to its fullest potential. Simultaneously, there has been obviously recently a really proliferation of AI methods and tools that do different things with data. They can predict, uncover, before predicting, really they can uncover complex patterns in data. Often single streams of data or multiple streams of data. They have actually the power to fuse data and understand patterns that are previously very hard to realize or understand. AI tools really also are pretty good with respect to predicting what's going to happen in the near future or even the distant future, based again on past patterns and based on current and existing conditions. Also, we've seen, the power of AI now that can generate content, can actually summarize content, and also can generate content, unstructured content, and so on from structured data. And so there is really so much power that's coming with AI that has not been leveraged very well in the area of public transit. And as I said, it really presents an opportunity that with all those methods, we can really try to utilize and harness the data, the rich data that transit agencies currently have. Add to this also newer technology that is enabling some kind of communication that was not really available in the past, communication between the infrastructure and vehicles, communication between vehicles and one another, and so on. And also those newer technologies are generating newer data. So, all of those really together, they have a lot of promise to help us really develop new transit solutions that did not exist before. So I'm going to share with you a few examples from our lab. I'm going to first start with some of the work that we've been doing, actually, not recently. When I first became a professor, one of the problems that I started working on is transit signal priority. And at the time, we applied, some methods that have become known as AI. So we have a long history in our lab working on advanced methods for transit signal priority. So I'm going to share with you some of our recent results and also some of our ongoing work on the application of AI to the TSP problem and also other route strategies. Let me start first with a little bit of history of TSP in Toronto. I'm not sure how many of you are familiar with Toronto, but Toronto, we always poke fun at the TTC and Toronto for the problems like we have in transit problems and so on. But really, to their credit, Toronto and the TTC have been pioneers in a number of areas, including TSP. So transit signal priority has started in pilot projects or pilot form in the 1990 on a single route, 501 Queen, which is a streetcar route, which really showed a lot of promise at the time with very simple track switching equipment and used for detection, very simple preemption algorithms and so on. But at the time, the pilot showed a lot of promise. So since then, fast forward to now, TTC has been gradually implementing TSP in various intersections. Out of the about 2,300 signalized intersections in Toronto, about 500 of them are equipped with TSP. This is really phenomenal. And the TTC has implemented in-house several TSP strategies like green extension, red truncation. So, I mean, this is the configuration that we have here. Do you see my laser pointer? Yes, no?
Yes, we can see it.
we see
Okay,
it.
perfect. Okay, great. Thank you. So this is the configuration that we have in Toronto for TSP. You know, this is a hypothetical intersection where the transit corridor is the north-south direction. You have for each approach, you have two detectors. The first is called priority request loop. The second one is priority cancel loop. Those are detectors buried in the pavement. And you have the traffic signal controller. And this is called the priority operating zone. If a streetcar is detected at some decision point within the cycle, then and it's green, then the traffic light really extends the green by 2 seconds and then checks again, and then another 2 seconds and checks again, and so on. So long as there is a streetcar or a transit vehicle here in the priority operating zone, either in this zone or in this zone, the green extension algorithm kicks in and gives, and there's another algorithm for red truncation, and then there's another algorithm for offset recovery. Anyway, it's really have been working very well. It's very simple logic. The impacts, TTC has shown that the average intersection can, the transit signal delays can be reduced by up to 10%, 10 to 15%, which means faster in-vehicle time for riders. And it's also, you know, shorter in round trip time or cycle time, which means that in some instances you can actually operate the same line with the same frequency, but with one or two fewer transit vehicles. So those are all good. Those are all good benefits. However, there are some issues, some problems that, you know, those algorithms are designed to minimize signal delays. They really do nothing to reliability. And some of those routes are high frequency routes. You know, the bus or the streetcar comes every 3 minutes or 4 minutes. And of course, with some variability, they can bunch up and so on. So the algorithms do not really, are not designed to tackle those operational problems. They are only designed to minimize signal delay for transit vehicles, which is good, but not sufficient. Also, there are some negative impacts on traffic, on the general traffic and the queues, because sometimes, you know, we have a near side stop and the streetcar or the bus really is stopping, is serving passengers on and off, and, you know, the green extension is kicking in. It really, of course, maxes out. Nobody's really utilizing this capacity of the intersection. So obviously it has negative impact on the general traffic. And overall, really, you have suboptimal corridor performance in terms of the person throughput. And also, there are some frequent operational problems, like we still see on those corridors where TSP is implemented, you still see bunching, you still see overcrowding, you still see, like problems and issues. So here comes our solution. We thought, okay, well, actually, let's try to design a more sophisticated TSP based on reinforcement learning, which is one field of AI. So this is, we developed something called D2 TSP, dual objective two-way TSP for isolated intersections. The main idea, those of you who worked with reinforcement learning before, they know it is really an agent that represents the brain of the traffic signal. And this brain can take actions. In our context here, the actions are either extend the green or shorten the green based on the state of the system. The state of the system here, we explicitly are really telling the agent the next bus that's arriving, whether actually it is running according to the scheduled headway, or if it's coming too early, or if it's coming too late. So headway deviation is part of the state, as well as the number of cars in the priority operating zone and so on. So you train this agent. Where do you train it? Well, you cannot really train it in the real world. You need to train it in a virtual environment. So we train it in a simulation model. Again, I'm sure many of you are familiar with simulation models like AIMSON and PTV, VISM, and so on. So you train the agent. Essentially, what you do is you expose this agent to, in the simulation model, where it's not really a big issue if it really makes a bad action, but you train it with so many scenarios that sometimes buses are coming late, sometimes buses are coming early, sometimes buses are coming on time. And you're allowing the agent to really implement actions in the simulation model. And then it then waits and sees what is really the outcome of this action. Is it better headway regularity? Is it less time in the priority operating zone, less time at the traffic signal, and so on? So over time, over millions of experiments, the agent becomes smart. This is really the whole. So the difference really in our case here from the simple TSP logic that the TTC implements is that we look really in terms of the state, at the headway deviation. We look at, how much traffic is there. And we look also at when the bus is coming within the signal. Is it coming during the green phase or the red phase, or what exactly? And the agent has been trained and trained and trained and trained in the simulation model. So it learns a good policy that, when in the real world now, this algorithm is implemented and I see a bus that's coming, 1 minute late according to schedule, and there's so much traffic, the best action is extend the green by this much or that much. So that's the policy. Okay. So this is really the overall architecture. There's so much, of course, details in there. By the way, anything that I present here, we have some papers on them. So if you want more details, I'll be happy to share them with you. So we tested this on one of the problematic routes in Toronto, 36 Finch West. By the way, we have about 19 or 20 high frequency, high demand routes. Each one of those routes is greater than 30,000 riders a day. This is really a very high levels of demand. So we have about 20 of them. This is one of them. So it's a high frequency route, headway of about, in the peak period of about 3 to 5 minutes, suffers from bunching and a lot of issues and so on. So we tested it on one of the intersections. So here are the results. So this is our algorithm, D2 TSP, and then there is the benchmarks are no TSP if the intersection really has no TSP at all, or the Toronto TSP, which is what we call unconditional TSP or absolute TSP. It sees a transit vehicle, it gives it the most priority it can. So it's very aggressive, of course, at the expense of others. And also, it doesn't really take into consideration headway deviation. That's the difference between, and then conditional TSP, which I'm sure some of you are familiar with. Conditional, you provide TSP whether, depending on whether the bus is late or early. If it's late, you provide TSP. If it's early, not. But it's really, it's just a binary decision. You know, if it's late by 15 seconds is not the same as late by 2 minutes. So, but in conditional TSP, those distinctions are not really clear. And then another benchmark, first come, first served. So when it comes to bus travel time in the priority operating zone, so our algorithm really does reasonably well compared to the Toronto TSP, which is, as I said, the most aggressive. Where it actually does well is when it comes to headway coefficient of variation. So because in our case, our algorithm actually specifically tries to regulate the headway. In other words, if a bus is really coming a little bit too close to the previous bus, it doesn't really give it priority. It actually may, in fact, try to delay that bus to build the headway back. So it improves the headway coefficient of variation. And when we look at extreme headways, very, very short headways or very, very long headways, ours is the yellow bar has really the lowest percentage compared to the benchmarks. So this is just an animation. Actually, this is the TTC TSP. This is our TSP at one intersection. So we see two buses coming here and two buses coming here. So ours, what it does, it actually lets the first go, and then it turns immediately into red. While this one actually doesn't recognize that there are two of them. So it actually gives the two the same green. So what we see as an outcome is that the headway deviation under TTC TSP algorithm is still really pretty bad. Yeah, maybe signal delay is reduced, but the headway deviation remains the same. But what we noticed is, one outcome is that, this is all fine and dandy in isolated intersections. To resolve reliability problems, you need really, if two buses are coming in a bunch and you want to break this bunch, you're not going to resolve this at a single intersection. You need to do it over multiple intersections in a coordinated manner. So we extended our work to develop something called dual and coordinated TSP, whereby you have multiple intersections and you try to actually coordinate the actions of the individual intersections in terms of the green extension and red truncation they give, so that if you have a bunch, you break this bunch. And in normal operations, you try to actually minimize headway deviation by having coordinated TSP actions at multiple intersections. So again, to show you the results here, here is our DTCSP, and this is the benchmarks. So going from one intersection to the next intersection, we actually see that the headway irregularity or headway deviation keeps improving, whereas with the benchmarks, it either stagnates or actually goes up. So it just goes to show the benefit of coordinating the TSP actions at successive intersections, which is not something that we do now. But with the help now with AI, as in our algorithm, you can coordinate the TSP actions over multiple successive intersections so that you can regulate the headway. So that's another result. So this is one example. What I showed you is one example of really applying AI, specifically reinforcement learning, which is trained in a simulation environment and then gets deployed into the field. Of course, we haven't really deployed it yet, but there is a pilot project that's going to start in January. And this algorithm that we developed here will be part of that pilot. So we'll see how it works in the real world, hopefully in the early 2025. Then we thought, okay, well, actually, let's now with AI, maybe we can think of other innovative strategies. So one of the problems is that sometimes the infrastructure, the traffic signal is providing priority to the bus or the streetcar, but the driver doesn't notice that. The driver is driving very slowly. So there is now the idea of driver advisory systems in which, the infrastructure can communicate a message to the driver and telling the driver, hey, I'm giving you a priority. Please travel at this speed. Travel at, 45 kilometers per hour to make it and to take advantage of the green. Or maybe it actually can communicate a message to the driver, you know what, you're not going to actually make it through the green. Why don't you wait an extra minute or so at the bus stop, the intermediate bus stop between your location now and the traffic light. So giving those advisory messages to the driver to minimize the stop and go. And of course, if this is an electric bus, of course, you would reduce battery consumption and so on. So we are currently working on applying AI to operationalize this concept of speed and dwell advisories, where the infrastructure will be communicating messages to the driver of what to do with respect to how fast they should be traveling or how long they should be waiting at the stop. And then we're also exploring now AI to implement something called dynamic or adaptive bus lane. Those are for simplicity, you can think of dynamic bus lanes. Are bus lanes really whereby the bus is operating similar to an emergency vehicle? The bus would be sending messages to a neighboring vehicle, clear the way for me because I'm coming. So, and hopefully with 100% compliance, the buses will pull out of the way and, the passenger vehicles or the general traffic will pull out of the way. So of course, to operationalize this concept, you need to decide, how long is this buffer should be? Should it be 150 meters or 100 meters or what exactly? So again, we're training some AI agents as we speak now to operationalize this idea. And also sometimes when you have multiple branches or multiple routes operating on the same corridor, you may want to give them all one TSP priority or action. Maybe you may want actually to get them to assemble them in a platoon and then give them all one TSP action. So bus platooning is also another idea that we're working on. And the idea is really with each one of those will be an AI agent. This will be an AI agent. This will be an AI agent. And this one will be an AI agent, plus the TSP agent as well. And then all those will be communicating with each other. So our vision for the future is, you assemble buses from different routes on the same corridor. You activate for them a dynamic bus lane where, this bus is sending messages to all neighboring vehicles, clear the way for me. And then the platoon would send a message to the traffic light, the traffic signal or the infrastructure. Hey, we're coming, give us priority. So the traffic signal sends back a message to the platoon, drive at this particular speed or wait at the next next stop this amount of time, and so on. So our idea in the future that, we will have those AI agents that we will be trying to optimize really the operation and the service for the benefit of the rider, so that you have shortest possible delay at traffic signals, regular headways, and also would optimize the operation for the operator by having buses, especially if they are electric buses, to spend as little time at the traffic signals, so minimize stop and go, which improves battery performance for electric buses. So this is the first example of application of AI to transit operation to improve route performance. So, and help us really develop advanced route improvement strategies. The second is some recent research that we wanted to focus a little bit more on anomalies. I know many of us researchers, me included, whenever really we get data from a transit agency, we try to clean up the data. We actually exclude data that has some anomalies like bunching and overcrowding and so on. But this is really part of the daily operation of transit routes. So we need to gain better insights and understanding of really those anomalies individually and how they actually interact with one another. So as I said, bunching over. So this is really the motivation of developing this tool that I'm going to talk about in a minute. So that bunching, overcrowding, and idling, and other anomalies like route deviation and so on, those are, commonplace. On some routes in Toronto, we have, 40% of the streetcars get short-turned in the opposite direction because of severe bunching. So, bunching and overcrowding and idling and other anomalies are part of the daily routine. So as we speak, there is really not, at least to our knowledge, that there is a tool that currently exists for analyzing those anomalies. To identify those anomalies, we get those AVL data and APC data, we don't really have tools to mine this data and tell me, this portion of the trip, there was this anomaly or that anomaly. So identification of those anomalies, analyzing those anomalies, visualizing those anomalies, we don't really have tools to do so. And, more advanced applications predicting those anomalies before they occur. Again, we don't really have tools to enable us to do so. So a number of, like about a year ago, we started working on this problem. So a PhD student, Jiaha Wang, developed what's called IROM. IROM stands for Integrated Route Operation and Anomaly Monitor. So as step number one, we wanted actually to have a tool that really can take on all the AVL, APC, GTFS data. GTFS, I'm sure you're familiar with it, is the route and schedule data, and AVL and APC. So it takes all of that, which really this is huge amounts of data for like a single route on a single day. And it can do all the pre-processing, and then it can actually identify and visualize the anomalies. So we, or Jiahao, developed this system here. Again, there's a lot of details that I will skip for now. Just to show you here, we tested this on one of the most problematic routes in Toronto called 29 Dufferin. It's one of the Toronto's high frequency routes. As I mentioned, we have about 20 routes that have ridership of 30,000 riders per day or above. This is one of them. It has about 43K before COVID. Suffers from all kinds of issues, operational issues, bunching, overcrowding, and you name them. And recently, it actually was named as the worst and the slowest route in Toronto. Traveling at about, on average, about 10 kilometers per hour during the peak period, and even off peak. So it's really pretty problematic route. So we got from the TTC data for a whole month on that route. Again, we're dealing really with huge amounts of data. AVL data about 6.2 million records, APC data about 0.6 million records, and GTFS data pertaining to that period. So this was relatively about a year ago, like in November 2023. So IROM can take from the user or prompt the user for the parameters for bunching, for idling, for overcrowding. And then it can, as step number one, identify and visualize. This is a simple time distance diagram, I'm sure, or you're familiar with it. And this is a map visualization. So, and then, those blue dots are essentially incidents of bunching. Green dots, which maybe you can see, you'll see them in a moment. Those are overcrowding instances. And then the red ones are idling. So you can, visually look at really, this is a playback of the trips that were taken on a day. Imagine if you have this data for yesterday, you can actually play back all the data, and you can actually look visually here. You see where the overcrowding is taking place, where the bunching, and you can actually start looking at patterns, that, maybe actually bunching and overcrowding are happening simultaneously. Which one really triggers the other? You can explore that using this data. One thing you probably I didn't mention is that, as this time distance diagram is being displayed, it actually shows at the top of each profile. Each profile, of course, is a trip trajectory, bus trip trajectory. So it shows the average speed. So it shows the average speed. But, the analysis part of the analysis part of IROM is that it can actually give you, let's say for yesterday, it can give you the box plot for the average speed for the whole day or for each time period. So we see, for example, in the evening, it is relatively higher than the peak periods. In the morning, like the evening period, peak period is the worst in terms of is actually a little bit higher than 10 kilometers per hour. The morning peak period is a little bit better, and the off peak or the midday is this is a busy corridor. But one of the fun graphs here is that it can actually decompose. IROM can decompose the trip into its components, and how much of the time the trip is actually traveling with no anomaly, like problem-free, essentially. How much of the time, in terms of percentage, it's bunching, how much of the time it's overcrowding, and how much of the time is idling. Of course, idling really includes dwell time at stops. It includes signal delays. It may also include some holding actions by the operator. So you might actually ask, where's AI in here? So what you've seen here is really step number one. What we are doing right now is really equipping this platform with AI, because what's not being shown is, actions that route supervisors take. If, let's say, there is a collision somewhere along the route, so then the route supervisor would instruct the driver to go off route, make a detour, and then go back. So this is an anomaly, right? And there is a service report written about it, right? Which we usually ignore. You can actually get those service reports. Some of them are online. Some of them you can get from the transit agency. Some of them are actually structured data, like in tables. Others are just written by hand. So well, there's so much really in there that we need to also integrate into IROM. So we are building a large language model that will actually get from those service reports whatever happened on a particular trip. Maybe the driver was instructed to hold at a stop for 2 minutes because it's too close to the bus ahead. So we are integrating, we're actually first extracting all those actions and then using a large language model. And then the idea is to, actually, let me just show you the whole thing. The idea is to have a large language model that is trained on the service, whatever really we see on those time distance trajectories, plus the service reports. So then it really realizes, okay, this action that was filed in this service report, for example, short turning or holding or route deviation, it resulted in this, outcome. So the large language model can really learn what the outcomes of different actions are. But so far, we kind of exclude those actions. We ignore them. We actually want to bring them into the picture in our case and train a large language model to really tell us, or to understand what the outcomes of those actions are. So this is incorporating large language model into this platform. And another extension we are doing is, maybe now we can, with deep learning, we can also predict anomalies before they occur. So for example, if we see two trajectories like this and you have overcrowding on those two buses, well, maybe like an intelligent deep learning agent will predict that maybe in 3 or 4 minutes, there's going to be bunching. It looks like they are actually headed towards bunching. So we're training a deep learning agent now to predict those anomalies based on historical and current conditions. So that's another AI capability that's being injected into iROM to help us really predict the future and specifically try to predict those anomalies. Okay. So the idea for this iROM is really to be an integrated system that help us, now in its current state, it can identify anomalies, analyze anomalies, visualize anomalies like playback or map-based. But then we are adding large language model to extract information from service reports and add them to really the platform and explain things. We might actually see, for example, that a bus was idling at some stop for 5 minutes. That cannot be just serving passengers on and off. So when you add a service report and you realize that, there was an action that was given to the driver at that stop to wait for 3 minutes or something. So you would actually know that, this idling is not strictly just serving passengers, but it's also a result of like a corrective action. And then understand, and then also with deep learning to predict, alert, and optimize. So the idea is really to transform this iROM from a monitor to become a problem solver, or problem-solving tool. Okay. The last piece of work that I want to share with you, I know I'm running out of time, is generative AI tools for transit. Specifically, we developed two systems. One is called Transit Pulse, and the other one is called Transit Talk. So Transit Pulse is very simply is a large language model powered system to leverage social media as a source for transit customer feedback. Essentially answer questions to the transit agency. What is it that passengers or riders talk about on social media? What aspects of service do they find satisfactory or usually unsatisfactory? I mean, when people tweet about something, it's usually negative. And where do they encounter those experiences? And when do they encounter those experiences? So this is another source of information or data that really transit agencies have not harnessed, have not leveraged because of the lack of tools to mine this data and extract useful information from it. So historically, of course, transit agencies, they do customer satisfaction feedback, they get customer input. Historically, they usually do like surveys, either physical, paper and pen questionnaires or online surveys to get feedback. There are so many issues with this. Social media is a great resource. It has broader reach. It has crowdsourced information, cost effective. It doesn't really cost anything for the transit agency, and it's real-time feedback. You can actually very quickly discover or realize, find out what transit riders are talking about your system today or yesterday, or and you have massive data set. So we actually worked in the past on this problem. We developed, the top right here is really a framework that we developed a number of years ago for Calgary Transit to mine their social media content. So semantic analysis, sentiment analysis, social network analysis, using standard natural language processing tools. So we had some issues. It was a useful system, and Calgary Transit still uses this system now, but it really had some limitations. One of the biggest issues really for traditional NLP systems is that it doesn't understand the context. It really has a hard time with slang. It has a hard time understanding shorthand text, um, complex linguistic environment, and so on. So it is really has some limitations. Whereas large language models, because really it uses advanced transformer models that really understand dependencies between and nuances of text. It has more advanced really features that can mine and analyze and extract useful information. Especially, it actually does a very good job with sarcasm. And tweets, social media tweets or social media content has a lot of slang in it. And when people really offer their opinions about public transit, NLP really, as I said, has a hard time differentiating between what's positive and what's not. So we developed this transit pulse. Essentially, it is really a large language model. I'm sure all of you or many of you are really familiar with ChatGPT and prompt engineering. So it has an engine where it gives a set of prompts, standard prompts to the large language model to inform the large language model what is really being asked of it when we enter a tweet into it. And then we actually have several attempts of interpreting a single tweet. So a single tweet, the large language models maybe have 10 different interpretations of it. And then we have something called like a consensus mechanism to really make sure that, the different attempts, we are getting the most common interpretations. And then we transform this into structured data. One of the issues was we wanted actually to understand the tweet talks about which part of the system, which line or which station or which stop. There are some tips in the tweet in most tweets, but really NLP really has a hard time figuring this out. But we know that GTFS, this kind of information is available in GTFS. So someone that is really spelling Bathurst as Bathurst. This is Bathurst. So, this is an exaggeration in a tweet. So if you actually embed this into like something called RAG. RAG is some feature in large language models in which you can actually find the closest name in GTFS to a name that you suspect is a station or is a route. So we added a RAG system, and the outcome was actually quite was phenomenal, actually, because we had the previous work we did using the NLP and then the large language work. And we actually used Llama 3. If you are interested in knowing the large language model we use Llama 3 because it's open source. And look, for example, at this tweet. So someone is saying, TTC, thanks for running the last Leaside side 56 bus and then telling me it will be here in 10 minutes. Well, you and I can probably figure this out that it is really sarcastic. A standard NLP will think, oh, they are saying thank you, so it must be a positive sentiment. But our large language model really realizes this is a sarcastic tweet, then it actually labels it as a negative tweet. So this is just one example. We have many more examples we can share with you. But the good thing about this is that, as I said, that the combination of finding out what problems people talk about, are they talking about accessibility, about communication, about maintenance, about ride quality or whatever, and also the location. So for example, you can actually construct a heat map like this. This is Bloor Station in Toronto, and those are the different kinds of problems. And over the time of the day, people talk, for example, between 8 and 9 about travel time. So the most frequent topic that they talk about is travel time. So you can actually construct things like this. The last tool I want to talk about is Transit Talk. It's another large language model powered system to make it easy and more fun for both the riders and the operator. So Transit Talk is really a suite, a system of digital assistants, if you wish. It really consists of three ones. The first one is called Tweet Writer. So Tweet Writer is essentially the communication staff at AMT or STM in Montreal or TTC. I mean, they write tweets. Service alert, whenever there's a service alert, there is, for example, bus breakdown somewhere, or that the bus is canceled or something like this, they need to write a tweet, right? So, and we see this, and those of us who are active on social media check really those tweets. So this could be actually, it's a repetitive task. And it could be also, maybe inefficient, that the communication staff might try to tweet late or write it really, quickly without really sufficient information. So we're kind of automating this step for them. So we are connected, this tweet writer is connected to GTFS RT. GTFS RT is a real-time version of GTFS, which really has all the service alerts and so on. Whenever there's a service alert found in GTFS RT, immediately the tweet writer really constructs a tweet. It generates a tweet. It can generate it in preset format, kind of standard format, or it can make it in open format and sort of fun-filled. If this bus route, for example, being affected is one that serves a lot of school students or university students, it might actually use a format that is more really appealing to them. But the benefit of this is that it really relieves the communication staff person with generating a tweet. It automatically generates a tweet from the information available, and then in the preferred format, and then the job of the communication staff is just to read it and approve it and then publish it. So all those tools have the same architecture, by the way. The second one is what we call Trip Advisor. So it is essentially a conversational trip planner. All of us are familiar with, the transit app or Google. If you want to go from point A to point B by public transit, you enter your origin and destination. It gives you the best path or multiple paths. So this one actually can do the same thing, but using conversational English. You can just, talk to it on your iPhone or your smartphone. Hey, I want to go from here to there, and then it will prompt you for questions. Do you have any specific requirements? Accessibility, for example, requirements. Do you have a bike on you or whatnot? So you have this conversational. So again, it makes it really easier for users to get the information they need in a simple format. The last application is called Policy Navigator, which is another large language model that really helps people to navigate policies. For example, can they take a bike on a bus during the peak period or not? This information is buried somewhere on the websites, but really very hard to get. So we're trying to make it easier for them. So, okay, what have we learned from all of this? We've seen that I've shared with you very quickly a number of applications of AI in different transit use cases. Well, the first thing that we actually found out that, there is so much data that in the past have not been used or not really fully utilized to their full potential, that now with AI, we can actually harness this data, both structured and unstructured data. All those service reports, the delay logs, if you talk to your transit agency, they have those delay logs that are written sometimes in handwriting, and nobody really uses this information. There's so much wealth in this information. AI can really harness this data, mix it with other kinds of data, and extract useful information from it. Another thing that we learned from our own experience using AI is that, in contrast to other methods, AI can effectively uncover complex patterns in data that you can there's when you look, for example, on a route like the 29 Dufferin, where you actually have both bunching and overcrowding happening simultaneously or one before the other, you actually AI can help you visualize and understand those complex patterns and how they relate to one another. Also, AI can help predict efficiently.
Think of questions with me.
Sorry?
No, someone unmuted by mistake. That's
Oh, okay. I'm about to be finished, by the way. AI, we found that they can actually also do a very good job with short-term prediction. We've actually done in a previous study prediction of passenger flows, short-term prediction of also bunching, and so on. So AI can efficiently and accurately predict what's going to happen in the near future and even the distant future. AI, in our case with TSP, it can actually learn from, in an experimental environment like a simulation model. It can learn complex and sophisticated policies and strategies for decision making. And it also has the capability of summarizing information, like summarizing all the contents of tweets, for example. And we have, people who tweet about transit in Toronto. We have about, 250,000 subscribers to the TTC X account. So it is really a huge amount of information. So large language models can effectively summarize information, can generate content, and so on. So there is really so much potential. So the usual question, AI is going to replace jobs and so on. What I would actually say is that AI is going to simplify some repetitive and menial tasks so that it can leave really the operator focus on the more creative and the tasks that require really thinking and require human judgment and so on. So AI can relieve the operator of like repetitive and menial tasks and help them focus really on more important decisions to make. It can also provide help with decision making. And it can also enhance and introduce new technical capabilities to the transit industry. So I don't really believe that AI and all those tools that we are developing are going to really replace jobs, but they will make the jobs of transit staff much better. So at the Transit Analytics Lab, which I direct, and we have here Brendan Hemley, who was senior advisor to the Transit Analytics Lab. We do a lot of other research that really span the full spectrum of strategic planning, tactical planning, service and operational planning, and operational management for transit decision making. We have a very extensive research operation covering different modes and different levels of decision making. I actually invite you to visit our website and also our YouTube. We have a lot of content on our YouTube channel about previous workshops and thesis and so on with individual tools. Okay, with this, I finish my presentation. So thank you very much. And I'll be happy
Thank you so much. Thanks, Amer. Thanks. Really appreciate it. Okay, we'll start with some questions from the room. So Tiago will help us with the questions in the room. And I can kick with a question because I have a comment and a question.
Sure.
So when you showed the time-space diagram of the buses and how it was moving automatically like that, I remembered I was doing this by Excel, by hand, around 20 years ago. So I know how hard it is to automate it. So that's a comment. I was like, oh yeah, okay. So that was like a wow moment for me because that was one of my first assignments is to do this time-space diagram.
Yeah. All of us had to go through this by hand.
Yeah, it was like a wow point for me when you put that. I want to ask you about the transit signal priority, because it's well known that the transit signal priority it works well on sometimes on the corridor, but it messes things up for the side corridors, for the side. It's like crossing streets or crossing routes.
Yes, yes, yes.
So did you look in any of this, of the crossing routes, how when you give priority here, what happens on the other side?
Yeah, yeah. Okay. Let me first tell you what happens here in Toronto, and then I'm going to tell you, our research, what we're trying to do. So here in Toronto, for the most part, when you have an intersection where you have its major corridor crossing a major corridor, where you have transit routes really on all four approaches, TSP is minimal there. Recently, the TTC developed a four-way TSP. So first come, first served. So the first bus to show up at one of the four approaches would really receive priority. And of course, the priority will be in the opposite direction as well. So they will have higher priority over the one. But for the longest time, TTC didn't actually implement TSP at those intersections with major crossing a major intersection. We definitely, I mean, the TSP algorithm that I showed you, I only actually showed it in one direction. The results were just for one direction, but it actually applies to all four approaches. So it actually looks, in fact, it actually looks at the person delay. So a bus that is coming empty, for example, it recognizes it's not treated the same as a bus that is full. So and then it takes into consideration the buses and their loads at all four approaches. So and the action that's taken is really to minimize the person delay on all four approaches. We even have an extension beyond this is to incorporate passenger vehicle delays, also in terms of person delays. So yeah, to answer your question, I agree that it can actually mess up the cross-street transit delays and so on. But there are some algorithms like TTC has a four-way TSP, and ours can deal with this problem as well.
With this problem.
Yeah.
Okay. Tiago, do you have, let's have a question from the room.
Who has a question? Anna?
I have two questions actually. The first one was, did you look at the energy intensiveness of these like AI activities? Like what are the emissions related to using AI in transit? And then the second one was just if there was security or like safety considerations, like sending messages to bus drivers while they're driving might be a safety issue. So those are kind of my two questions.
Yeah, well, thank you very much. We recognize on the first question. Well, obviously AI can generate emissions. We know that it's not something that we have looked into. Yeah, I think for full accounting of the benefits and the impacts of AI, one has to look at the benefits plus, of course, the negative impacts like the one you mentioned. But yeah, maybe that's something we can consider in future research. And others. I'm not really aware of others who've looked into this specific aspect, but if you've come across any research that really looked into it, I'll be very interested. The second question is, well, definitely, whatever speed advisory we are giving. Of course, we have not really implemented this in the real world, but we are cognizant of it. That obviously that the speed really has to be within the minimum and the maximum. Whether in fact really the driver, how much they will comply with it. It's an advisory message. So because you want to actually make sure that the bus can take advantage of the priority it's being given. You advise the bus driver to please speed up a little bit, travel, speed up to, let's say, 40 kilometers an hour or 50 kilometers an hour. So whatever really speed advisory is given is definitely supposedly a safe speed. It's within really the limits of, we will never give really a speed advisory that's beyond the speed limit, for example, on that particular corridor.
Okay. We have a question from Iowa coming from Bogdan. So he's saying, thank you for the insightful presentation. He's curious to hear your thoughts about the application of AI. So you are working with TTC where they have a lot of data. And
Yes.
whereas there's rich amounts of data, what about the places where there's no data, where it's like, how can AI help a place like Whitehorse Transit, for example, with only 15 buses?
That's actually a very good question. Yeah, I mean, even here in Canada, the vast majority of transit agencies are small size. We have very few large size, Toronto, Montreal, Calgary, and then, small, mid-size, and then, the vast majority are small size. One of the things that we are actually thinking of is, a place like the TTC and maybe STM, and they have a lot of experience. We're trying to actually kind of codify this experience. I mentioned, for example, the service reports and the delay logs. There is so much knowledge in there. Perhaps if we can codify this knowledge in a large language model, and then you give this large language model to a small size system that doesn't have a lot of experience. And then their staff can actually probe the large language model. If I have this situation, what should I do? So, of course, it will require, of course, some human judgment on their part and so on, but at least that we can actually kind of transfer knowledge from big systems with rich experience into smaller systems using just simply a large language model. So I think there is so much for AI to offer small systems as well.
Ahmed Nawi is asking you, that's not an AI, that's a TTC question. So he's saying, shouldn't the 29 Dufferin bus route be converted to BRT system?
I said we have 20 bus routes. We have actually, 20 surface transit routes. I think about 7 streetcar routes and 13 bus routes that are really very high demand and like Dufferin. Well, I fully agree. I mean, many of those routes really we need to do something. We need to upgrade them to higher order public transit, BRT or LRT. Those things cost money and take a lot of time, especially in our case here in Toronto. It takes forever to build an LRT line or BRT. So, and of course, it's the whole process is really mired with political decisions. And so it's, technically speaking, I mean, a bus route that really serves 30,000 passengers, or sorry, in the case of 29 Dufferin, 45,000 riders every single day, it warrants dedicated lanes at least, and BRT or LRT.
Okay. It needs a political will.
Yeah.
Generally.
Yeah.
Any questions?
Okay. No questions?
No questions. No questions.
Okay. Thank you so much, Jaime. I really appreciate it, and really appreciate that you took the time right after your class to come to us. And we should have a long discussion about the customer satisfaction and the stuff together at some point, because we should collaborate. We keep saying we have to do it, but we'll have to do it now. I think it's about time.
Absolutely.
So thank you so much.
So next time we invite you as well here at U of T to tell us about your exciting research, and then we can find the opportunities for collaboration.
Okay. Thank you so much, Jaime, and thanks for those who are joining us online. I'll stop recording.